Hey everyone, welcome back. Last video we did the energy portion. Today we're going to do the free body diagrams and sum of forces and moments for this second worked example. I've gone ahead, I have the diagram for the mechanism here on bottom. Remember that there are, it's a big disc, a little disc, two connecting rods, a block sliding on a slope, and then one block translating vertically. If we're going to do, here, go in there. There's something interesting in there. If we're going to do sum of forces and moments, we have to do free body diagrams. Remember, this diagram is not a free body diagram. Free body diagram means all of the parts exploded. So here then are the 6 bodies, A, B, C, D, E, F. Before we do the equations, let's just go through and let's put all the forces on these diagrams. Now, what's the easy stuff? Easy stuff is gravity. We know that there's gravity on every one of these bodies. We can go through and we can do them all at once. MAG, MFG, BG, CG, DG, and MEG. There we go. You don't have to do them all at once. You can do them one at a time if you want. It's up to you. Gravity is an easy and obvious one, so all the bodies have gravity. Next, what are some other easy ones? Well, we know that there's going to be reaction forces at all of the joints. Anytime you have a joint and that joint provides some kind of constraint on the system. It takes away some local motion. There needs to be a reaction force on the diagram enforcing that constraint. So, for example, take the big disc. The big disc is pinned in the middle, right? And this pin joint in the middle takes away local degrees of freedom. It prevents the disc from sliding left and right, which means that there is some reaction force in the left and right. And it also prevents the disc from moving up and down, which means there is some reaction force in the vertical. I'm gonna call this R1. So it's a set of reaction forces, R1. So we could say R1 in the X component, R1 in the Y component. Now, what frame do these R1s need to be in? They could be in the A frame or they could be in the N frame. I'm going to end up putting them in the N frame, but you could get away with A frame. And we need to do the same thing for any joint in the system. So the pin joint is a particular type of joint. What are the other joints? Well, there is the rope that connects the big disc to the vertically translating block. And that is technically a joint, and there is going to be some tension in this cable. Now, whatever tension is in the cable, whatever tension acts on the big disc, it does, of course, act on the sliding block as well, so we could go ahead and add it to the sliding block. Notice that the magnitudes are the same. I call it capital T for tension. And notice that the arrows are acting in different directions, right? Equal and opposite reactions. Yeah, you having fun down there? Good. What are the other joints? Well, the big disc is interference fit with the little disc, right? We talked a bit about what interference fit means. It means these two bodies, the coating around the outside, some kind of hard rubber, has been compressed just slightly, and then these two discs were mounted, and there's contact between the two discs, and they're being pushed against each other, which leads to a friction force. Now, if they're being pushed against each other, that means that there is some force between these two. So this force between them is akin to a normal force. Consider that with this lower disc here, this big disc is prevented from translating into the lower disc, right? So the lower disc pushes back. So this was R1. Let's call this R2. Because again, it is a reaction force, it's a normal force. Along with this R2, there is going to be some Coulomb friction. And remember, equal and opposite, right? So if we put it in a particular direction on body A, it has to be in opposite direction on body B. Next, what else is going on with A? Normal force, friction force, reactions here, tension, and gravity. Okay, as far as what has to be on the diagram, that's good for body A. Now, what else could be on the diagram? You could have friction at the pin joint. There could be some kind of rotational friction. I'm going to say for today, let's not worry about it. I'm not going to include that on the exam that's coming up. We will continue to do more with friction and more with forces and moments, etc. Now, so I'm going to say that that's good for body A. What about body F? Well, body F has the tension in the cable, and it has its own gravity, and unless there is something else external acting on it, this is it. Now, what else could be acting on block F? It could be swinging left and right. It could have some other complex motion. It could have air resistance, right? You could model some viscous friction on it. And again, we're going to get into some specifics on how to do that later. For right now, this is fine. Let's move on to B. So body B, we already have reaction number 2, this normal force acting on it. We have this Coulomb friction. What else is going on with body B? Well, body B is the little disc, and there's pin joints through the middle. I'm going to draw it like that. I'm going to call that set R3. And then also, there are pin joints. There's a pin joint there at that connection between the smaller disc and the first of the connecting rods. There's a pin joint there as well. So at that pin joint, I'm just going to draw it like this. There is another set of reaction forces, R4. I think that's good for the little disc. Again, unless there's something else external acting on it, or if there was friction, something like that. So I think this is okay. Let's move on to the next body, the first connecting rod. There is, of course, the pin joint on the left side. That pin joint is attached to the small disc. We chose R4 to represent those reaction forces, and then I drew the arrows to the right and up. That's going to make the arrows left and down, which just is implying negatives, and then R4 at that bottom left corner. Now, we've already put gravity on body C. All that's left is the pin joint between the two connecting rods. So this is R4. Let's call the next set R5. We already have gravity, so we can move on to body D. As we saw with the previous one, this pin joint is shared by body C and D. We called it R5. It's to the right and up. So here on body D, it is to the left and down. This is R5, the same R5. Okay, what else? We got gravity. We have another pin joint on the right side of D. That would make that R6. That pin joint on the right-hand side of D is shared with body E. It is right through the middle. We chose these to the right and up, so we choose these to the left and down. And that's going to be R6. Okay. So bodies C and D look good. Again, there could be air friction acting on these. Maybe this mechanism is swimming in engine oil, something like that. That's going to create a little friction. What do we want to do on body E? Well, first thing I'm going to do is I'm going to move the gravity force to just make this a little cleaner. I'm just going to draw gravity acting here on top. It's through the center of mass. That's the important part. What else is going on with block E? Well, block E is on a surface, and there are constraints associated with that surface. Even though it's at an angle, it's at a slope, the block cannot move through that surface. So it's prevented from translating in that direction. So that's the constraint. The constraint is it can't move this way. And because there is a constraint, there has to be some reaction force enforcing the constraint. So here's body E. The constraint is that it cannot move into the surface, so there has to be some reaction force pushing it back. R6, so this is R7. So again, R7 is it's a normal force. Now, we had a Coulomb force between the two disks. Let's go back and call that one Coulomb force number 1, because we can see that there's going to be some sliding friction on this block as well. I will draw it like that, and I'm going to call this FC2. Coulomb friction 2. So there's some kind of sliding friction here, and there's some other kind of sliding friction here. Okay, good. I think that's it. I think that's it for these diagrams. We'll see. I might have to come back and edit this in a bit, but we've got gravity on all of them. We've gotten the tensions. I think we've gotten all the pin joints. We've got normal and friction. We've got normal and friction. Okay. I think this is good. Here's what we're going to do. I'm going to clean this up. I'm going to put one of these bodies at a time back on the diagram, and then we're going to write sum of forces and moments, and that's it for the problem. Sum of forces and moments for body A. Here's the diagram for body A. We need to just write some equations, okay? Let's start with sum of forces. So we're looking at the sum of forces on A. Now, some of these are very clear. Gravity is always an easy one. Minus MAG, Y hat N. What else is easy? The tension in the cable. We can assume that the block is always moving up and down, right? It's not swinging side to side. That means that the tension is always acting in the Y hat N direction. So we drew it down. I'm going to say minus T in the Y hat N. Okay, that takes care of gravity, that takes care of T. Next, let's do reaction force number 1. We get to pick what frame these reaction forces are in. Honestly, let's just do the in frame, right? In absence of some reason to do something else, let's just do the in frame. Plus R1x, x hat N, plus R1y, y hat N. Okay. What is next? So that takes gravity, tension, R1. Okay, so all that's left then is this normal force and this Coulomb force. So what's the proper way to handle these two terms? Well, we already have symbols written for them. We know that we can go back and we can replace FC1 with something else. The big concern here is working out the directions. R2 is normal between disk A and disk B. Consider that the direction of R2 is always fixed, right? It's a vector pointing from one center of mass to another center of mass. It's not any direction in the in frame, unless these disks are perfectly aligned, like vertically or horizontally. So this isn't an in direction. It's also not A frame or B frame, because A frame is spinning and B frame is spinning. So neither X hat A nor X hat B or Y hat A, Y hat B, none of those are appropriate for the R2 direction. What is best to do here is to just define some other frame. It's a non-moving frame. It's offset from the in frame by some fixed angle, and we can just draw it. And let's call this one, we've already been through bodies through E, G. We can call it the G frame, why not? So this direction is X, X, G, and here is Y, G. Okay, if we do this, we use these, then the forces R2, so plus R2. R2 is acting in the xg direction. And then I picked a direction for FC1. FC1 is acting in the negative yg direction, that's fine. So let's just do negative FC1 in the yg direction. Okay, so this is just the sum of forces, right, for the diagram. The only really tricky part here is recognizing or sorting out what to do with reaction force 2 and Coulomb force number 1. Next. Given all of this, can we now come down and can we sort out the details of sum of moments on A about A? Remember, we're taking the moments about the center of mass, right? And then looking at the diagram, which of these forces even create moments about the center of mass? We know by definition gravity does not. The reaction forces are one, they're acting at the center of mass, so there is no moment arm. The reaction force R2, R2 actually points towards the center of mass, right? So R2 creates no moment. All that leaves is the tension and the Coulomb force, right? Those are the only thing the only ones that leaves. So let's say this is P, the position vector. Now, the center was point A, and just to make this easy, for now, let's call the points where the tension is attached, we can call that one A prime, and the point where the normal force R2 and the Coulomb force FC1, this point where they attach, we can call this one A double prime. You can cook up other letters, call it whatever you like, but we need the position vector from A to A prime. That's from the center of the disk to where the tension is attached. So from A to A prime, cross, remember moments are cross products, and then it is cross the force. So the force is T acting in the negative y hat in direction. I'm just going to say negative T y hat in. And we'll come back and we'll sort out what this position vector is. The other moment, we need the position vector from A to A double prime. That's simply the point, right? The point where this friction is applied. And we're going to cross. Now, what's the friction? This was how I drew it. This was how we backed it up with the equation. We defined it. It ended up being in the negative y hat g direction. That's fine. I'm going to say minus FC1 y g. Okay. Next. Sum of moments, A about A. What are we going to do with these position vectors? Well, we're doing a cross product. It would be really nice doing your cross product if your position vector and your force are in the same frame, right? So that we don't have to do any rotations before we cross product. Ideally, PA to A prime is in the end frame then. Okay, that actually works because from the center of the disk to the point where the tension is applied, no matter how the disk spins, right, whether it's rotating positive, rotating negative, this position, this point where the block is then hanging ends up always being constant. So we can go a negative. We're using the radius. Remember, for this problem, we define them as capital R's. And this is the inner radius of disk A. So we called that one R1. Now, I wrote it as negative R1 in the X in, right? And then just bring this down, minus T in the YN. Okay, next. This force is in G frame. We would really like it if this position vector was also in G frame. We're going from the center of disk A down to the contact point. Well, conveniently, that one is, that's in the XG axis. We need to go from the middle all the way to the outside. This was the radius of A, and it was the second one. And we're actually going against the xg axis, so I'm going to put a negative on that. So minus rag xg, and then we're crossing minus fc1 yg. Okay, let's see how this comes out. Sum of moments, A about A, and let's fix all these cross products. X hat n, Y hat n. X cross Y is positive Z. There's a negative and a negative. These both become positive. So it's the scalars. Let's say R, this was RA1, sorry, RA1. RA1 multiplied by the tension, and that is in the positive Z, so I'm going to say Z hat A. Next, we have X cross Y. X cross Y is positive Z. These are both negative, so we end up with the scalars RA2 multiplied by FC1, and that is also in the Z hat A. You could factor out the Z hat A if you want to, and you can group these terms. Now, does this expression make sense? or let's go back and evaluate it, right? Let's always take your results and confirm that they make sense. Look at how we drew the picture. The way that we drew the diagram, I assumed a certain direction for the tension, and I assumed a certain direction for FC1. If both of my assumptions are correct, if tension does in fact point down, and if FC1, because of however this thing is moving, does in fact point in this direction, this tension we can see would create a positive moment, right? This friction force would also create a positive moment. So when we look here at the math, this expression says positive moments, right? Now, is that always true? It could be during some kind of operation that this disk is spinning in a different direction, so the direction of the friction force reverses. If that happens, the sign of FC1 goes negative. And when it goes negative, this distance is a constant, but when the friction points in the other direction, you end up with a negative moment. So this expression actually takes care of that. If the friction ever reverses, this will automatically generate negative moments about the center of mass. Okay, good. Write this down. Let's move on to the next body. Body F, all it is, it's a block moving up and down. Tension in the cable, and then gravity acting on it. Sum of forces on body F, we only have these two. Tension is acting in the positive. Y hat n, gravity is acting in the negative. Gravity, of course, acts through center of mass. And the tension is acting on a line passing through the center of mass. So, really by observation, we can claim that the sum of forces on F about F are 0. Okay, this one's really easy. I am going to I'm just going to interject one comment and then we're going to move on. I'm going to ask the question, is this true? If I say that the tension is equal to MFG, is that true? Some of you might be inclined to say yes. If you look at this equation, the first one, you can move gravity to the other side. No, though. The answer is no. The tension in the cable does not equal gravity. And the reason it does not equal gravity is because recall that the sum of forces is equal to ddt of K, which really means T minus mg, mfg, is going to equal mf multiplied by q2 double dot in the y hat n. Now, we haven't gotten into this part in detail, but this literally is, this is the equation of motion for this block. Now, notice we don't know what the tension is. The tension is currently an unknown. If we wanted the final equation of motion, we would have to get rid of T. And we're gonna work several problems where we go through the whole process of getting rid of these unknowns. But for the question, is the tension equal to gravity? Tension is absolutely not equal to gravity. This time, take MFG and move it to the other side, and the tension, if you solve for it, is equal to this. MF multiplied by Q2 double dot plus G. And I've dropped the y hat in description. This whole equation is in the y hat in direction, so I basically simplified it down to a scalar. What does this equation say? This equation says that the tension in the cable is equal to gravity plus whatever acceleration the block is experiencing. So if the block is moving up and down, if it has some kind of acceleration, that actually affects the tension in the cable. It can contribute to or take away from the tension in the cable. So don't be fooled into doing this. When you do that, say the sum of forces is equal to 0, that's a statics problem. So we cannot simply say this one is equal to 0 and then make this claim, because again, it's a dynamic system. So we're going to see more of these details in the future. Body B is the little disc. I've redrawn the image. We know that there is there was this normal force R2. There's the contact friction FC1. There is my cat. There is gravity term. There is the reaction R3 through the pin joint. There were 2 sets of pin joints, one through the middle and then one at the connecting rod, and then gravity. Now, we saw it in body A. R2 and the Coulomb friction force, these are defined in a non-moving frame. We called it G, XG, and YG. Okay, so sum of forces on body B. Next, we just take the forces, write them in. As usual, let's start with gravity, knock that one out. NBG in the negative, y hat in direction. Next, R3 and R4. Let's just stick with the previous convention. For this problem, let's put all of these reaction forces in the in frame. Both sets are positive on this body, so that's plus R3x, xn, plus R3y, yn, R4x, xn, and R4y, yn. Okay, gravity, R3, R4, good. Next, what do we want to do with the R2 and the FC1? Well, in this case, R2 is pointed in the negative xg direction, so minus R2 xg, and then this time FC1 is acting in the positive, so plus FC1 in the yg direction. Okay, that's literally it for the sum of forces, right? You just go from the diagram and you copy everything in. Next, which of these forces create moments? Well, friction force is going to, R2 is pointed at center of mass, R3 acts at center of mass, and MBG acts at center of mass. So again, those don't. However, R4, reaction force number 4, both of those create moments, the R4x and the R4y. Now, you could find some clever way to define R4 perhaps in B frame, such that one of these is always pointed at the middle, and that would simplify it down a little bit. But if we put R4 in B frame, to make it easy in this problem, when we get to the next body, those forces are still in B frame, and that makes that process more complicated. So I'm going to say for now, let's leave these forces as they are, and just recall the ones that are going to create moments are going to be FC1, and then R4. Okay, so on the diagram now, if the middle is point B, let's call the contact point B prime, and let's call this pin joint, which we're going to treat both of these like they're at the same distance. We made the assumption that it's just a fixed radius and they're at the edge. But if this is point B, this is point, that's B prime, that makes this one B double prime. And again, we could give them other names. We could call them Greek letters or numbers or whatever you want to do. That's fine. Okay, you have this one in your notes, sum of forces. Let's write now the sum of moments about this center. So we're looking at the sum of moments on B about B. Okay, and the ones we need to do are the friction and R4. So the friction first, we're looking at the position vector from B to B prime, and we're going to cross. This is FC1 in the Y G direction, plus the position vector B to B double prime, cross. And we have R4X in the XN and R4Y in the YN. Okay, let's sort out these position vectors. Sum of moments on B about B is equal to, all right, position vector from B to B prime. This is in the XG direction. It's actually a fixed distance, right, in a non-moving direction, so it's really a constant. We called that one RB, radius of B, and this is in the, again, this is in the XG direction, and we're crossing that with FC1 in the Y at G direction. Good. Next, plus the position vector B to B prime. So B to B prime. Now, one thing to take note of about B prime is B prime actually goes around. As this disc spins, the mounting location for the connecting rod is on the edge, so it goes around the outside, which means the best way to get from B to B prime is to use the rotating B frame and just orient the B frame from B to B prime. So we can say it's the same distance, RB, and it's RB acting in, let's call it the XB direction. So it's XB cross, and then it's cross this same previous claim from before. So R4X, XN, and then R4Y, YN. Okay, I'm going to erase the portion on top, and we can sort out these details. So sum of moments on B about B. This first one, X cross Y, is positive Z. So just bring in the scalars. RB multiplied by FC1 in the Z. Let's make it ZB. In the ZB direction. Good. Next, what do we need to do with these? Well, the position is in B frame and the forces are in N frame, so we need to convert. We can very easily convert XB into the N frame. We've done this several times. So I'm going to say plus, and it's plus RB multiplied by cosine theta 2 x hat n plus sine theta 2 y hat n. It is this quantity cross these forces, R4x xn and R4y yn. Okay, so the first cross product we actually took care of. Second cross product, we need to do a conversion first. Let's finish this. RB, I'm just going to copy this first one down. RB FC1 ZB plus. Okay, what's going to happen on the next cross product? Clearly, we can distribute the RB, so we get these two terms cross these two terms. It's x hat n, y hat n, cross x hat n, y hat n. You can distribute the cross product. You can actually do a FOIL expansion on this. You can take the first one, and then you multiply both of those, and then you take the second one, and you multiply both of those. When you do that, it's x cross x, which of course goes to 0. And then we're going to have y cross y go to 0. So really, it's the x cross the y portion, and then this y cross that x. So let's say x cross y is going to give us positive z, so we can just write out the scalars. Radius b cosine theta 2 multiplied by r for y, and that is in the positive zb. The next portion, this one's going to be y cross x, which is a negative z, and then we just bring down the scalars. So it's negative rb sine theta 2 r for x zb. And there we go. As always, check this. Does this make sense? Do we agree with this? This first term, RBFC1, so we're looking at the friction force. Again, when you do your free body diagrams, you pick which direction to put these arrows. And if at some point in the dynamic analysis, the friction is actually pointing the other way, well then the value just switches, right? The sign goes negative. So if we assume FC1 is positive as we have drawn it, that's going to create a positive moment, which makes sense. Again, it would make your disc want to spin this way. So that's a positive moment. Next, how should we understand these with the cosine and the sines? Well, R4 we're saying it is acting in the in direction, right? X hat, this one's in, the Y hat in, this one's in X hat in. If I were to take, as it's shown right now, and I were to say that R4X was a positive force, you can see that would also make the disc want to spin in a positive direction. Similarly, if R4Y is positive, that would want to push the disc in a positive direction. Now, what if the mounting location was not here, but on the other side of the disc? Then a force in the positive X end would create a negative moment. And a force in the positive Y end, if the mounting location was here, that would also create a negative moment. So even if the forces themselves are positive, depending on where on the disc is the current position of the mounting location, right? Sometimes it'll be positive, sometimes it'll be negative, and that is taken care of by these trigs. The cosine and the sine of theta 2 is specifying where on the disc the contact point is, and then of course these sometimes will go positive and negative. Okay, this looks good. So this was body B. Let's do body C. Here's the free body diagram for body C. Body C is fairly easy. There are two sets of reactions arising from pin joints, and then there's gravity. Let's write the forces. Sum of forces on body C. Let's do gravity. Minus mcg, y hat n. We have two forces coming from R4. Remember on the previous body, these were selected as positive. So on this body, they're negative. These are in the in frame, minus R4. It's minus R4x. xn minus R4y, yn. Now, forces at the other pin joint, R5. We're going to take these as negative. We'll take these as positive. They will be negative on the next. R5x, xn and R5 Y, YN. Good. Okay, there's the forces. Let's do the moments. This is C about C. Okay. Gravity creates no moment. We can see that both R4 and R5 will create moments. And then we, before, had called out these lengths. We had called this one L2 and then that one L3. L3, no, L1, L2, sorry. L1 and L2. Okay, good. So if the middle is C, the point on the left is C prime, the point on the right is C double prime. Again, call them whatever you want. We need the position vector from C to C prime, cross, minus R4X, XN, minus R4Y, YN, and then the other one, position vector from C to C double prime, cross, and this is now R5 in the X and R5 in the Y. Good. Okay, let's sort out these position vectors and let's see what we got to do. Tell you what, before I rewrite the whole thing, I'm just going to write the position vectors here underneath. So here is P, position vector from C to C prime. C to C prime, center of mass down to the bottom left. We're going a distance L1. We're going in the opposite. We had, go back and look at how we did position vectors. We called, that direction was XC. So this is minus, it's a minus L1 in the X hat C. And then this other position vector, C to C double prime. Remember, why is this one slightly more complicated? We are not assuming that point C was the geometric middle. This is just a slightly more generalized way of saying that the center of mass can be anywhere along this length. So if we want to go from C to C double prime, that's the center to the top right corner, that distance is going to be L2 minus L1. This is going in the X, C direction. Okay. All right. So sum of moments on C about C. We need to take this first one, we need to take this first position vector and we need to cross the forces. We need to take the second position vector and cross the forces. We can see what's going to happen. We had to do something similar on the previous problem, right? We need to put everything in the N frame. So I'm just going to convert the C frame position vectors into the N frame. So it's negative L1, and this is going to be cosine theta 3 xn, sine theta 3 yn, and that is cross. I'm just going to write cross R4. We know what that means. We know that R4 is equal to this. And then plus, what? L2 minus L1, and that's cosine theta 3 xn sine theta 3 yn. And then it's this term cross R5. Okay. So what's going to happen when we do this? I'm going to erase the stuff on bottom. So in each of these, we're going to have x cross the z term, x cross y. Sum of moments, C about C. If we do the x cross y terms, we're going to get positive z. Now, for this one, there's a negative in front And on the R4, look at your notes, the R4 is negative in the X and negative in the Y. So we're gonna take this X and we're gonna cross it against that Y. It's negative here, it's negative here. That's gonna make it positive. We're looking at L1 cosine theta 3 R4Y. And I'm going to group everything since we know everything's going to be about Z. I'm just going to group it all, and we'll put in the Z at the end. Next, we've got Y cross X, the X term that is inside of the R4. So Y cross X is going to yield negative Z. It's negative here, which makes it positive, and then it's negative X, which makes it negative again, right? It's Y in cross the X in term, which itself is a negative Z. Negative, negative makes it positive. The next negative makes it negative again. So minus L1 sine theta 3 R4X. Okay, next, moments created by R5. Now, how different is this going to be? Well, we just have a positive position vector this time, right? Before it was negative L1, this time it's L2 minus L1. So the first term, here's what we expect. The first term is going to go negative and the second term is going to go positive. That might be what you expect. However, don't forget that the directions on R5 have also been switched. So again, look in your notes. You have all the details in your notes, but we have some scalar distance. We have cosine, and it's going to be X cross the Y component here, and X cross Y is going to be positive Z. So I'm going to bring down the scalar component plus, and this is L2 minus L1, cosine theta 3 R5 in the Y. We're going to have scalar distance. We're going to have Y cross X. The X term itself is positive. Y cross X is inherently negative Z. So this is negative L2 minus L1 sine theta 3 R5X. And we got a couple sets of parentheses, so I'm going to bracket this ZC. Hey everyone, I started doing body D, and then as I was doing it, I realized that it's the same thing, right? You change some of the numbers. Now it's R5 and R6, MDG, and you can change the links, L3 and L4. But you will find that you get effectively the same thing for body D that we got for body C. So I literally just took that equation and just rubbed out the indices and wrote in all the new numbers. So by all means, feel free to do this one, right, and work it out and just confirm that you get the right answer. And again, check my math. I might have made a mistake, but body D just like body C. Okay, let's move on. Do the next one. All right, everyone, last one, body E. Here's the free body diagram for it. Remember, there was reaction force set number 6 from the last pin joint. It has its own gravity. There's a normal force, R7, and there is a Coulomb force, number 2. Now, this block is moving along a slope. Let's draw the frame for the body itself to help us out. Here is XE, and this other one is YE. Okay. Okay, sum of forces on E. Let's bring in gravity, minus MEG. We can bring in reaction set R6. These are negative, so minus R6 X in XN, minus R6Y in YN. Next, R7. So R7 is normal, right? It's not in the Y head in direction. It's a function of the geometry of the surface. Now, I put the E frame here to help us out. Notice that reaction 7 is going to point in the Y hat E direction. So we can say plus R7 YE. Similarly, the Coulomb force, it's on the surface, right? So that is inherently in the XE direction, plus FC2 XE. Okay. Next, we just got to do the moments now. So sum of moments on E about E. And as always, ask yourself which forces create moments. R6, the reaction set 6, that's at the center of mass. We're assuming the pin joint is through the center of mass, so no moment there. Obviously no moment from gravity. The normal force, we're going to treat the normal like it's acting at the center of the bottom surface, and it is normal to the surface, which means it points at the center of mass. Again, these are all assumptions that we make to simplify. And then we're just left with the friction, moment created by friction. So let's say P, we're going from E, I'm gonna call that reaction point E prime, where the friction force is applied, cross FC2 in the XE direction. Okay, what's this gonna be? Well, this position vector, let's just give it some length. We're up to length 5. So this is L5. Notice we're going in the opposite, right? We're going in the negative Y hat E direction, cross FC2 in the XE. Okay, so this one's fairly easy to see what happens. Y cross E is positive, sorry, Y cross E is negative Z. There's a negative here and they're going to cancel to make it positive. So the sum of moments on E about E is equal to, we can take the scalars, L5, F, C2, Z, E. Which again, go back and look at the diagram, ask yourself, does that make sense? That these are going to create a positive moment. Here on the diagram, there's the friction force that's acting along the bottom. That would make the block want to rotate in a positive direction. Okay, good. So this was sum of forces and moments for all of the bodies. Couple last comments before we get out of here. In this particular example, I am not worried about solving for FC2 or solving for FC1. Based off of what we've talked about in previous videos, you could probably sort out the FC2. FC2 is going to be a function of R7, right? It's going to be a function of the velocity of the block, and it's going to be a function of some coefficient of friction. Now, the tricky part in this is understanding how do you figure out the value of R7? Because again, this block is at a slope. It is not, R7 is not going to equal just gravity because there's also R6 acting in the vertical, and R7's at an angle anyway. So clearly this becomes much more complicated to solve for FC2 in terms of R7 because it ends up being a very dynamic problem. So we're not particularly worried about replacing the friction on these. And if you go back and look at FC1, that was a rotating body, which we haven't talked about in great detail yet. All that is required right now is that you can write these equations. If you are unsure of how to replace these, we're going to get more practice in that as we move into equations of motion. Okay, I think that's it for this problem. As always, best of luck. I will see you next time.